So this is going to be the last topic of the course, engineering structures. Now, engineering structures are typically an assembly of rigid bodies which is meant to withstand a large amount of load, large amount of force. The structure has the capability to withstand large amount of force. Again, in a regular semester, I like to cover three types of engineering structure. First is what we call as a frame. The second is what we call as a truss. And the third is what we call as a beam. Frames, trusses and beams. I am left only with about 40 minutes, 45 minutes. I won't be able to cover trusses and beams, but I do want to talk about frames. The topic is actually analysis of frames. But what is a frame? Let's first define what a frame is. A frame is an engineering structure which is comprised of several individual rigid members connected by pins. However, there is at least one member with at least three forces acting on it. Let's keep it like that. There is at least one member with at least three forces acting on it. Okay. So not all members are zero force members. Not all. I think that's the other way to write. Not all members are zero force members. In fact, this is the distinguishing feature of a frame and a truss. In a truss, all members are zero force members. Okay, whereas in a frame, not all members are zero force members. What I have written here is the other way of saying the same thing. There is at least one member, at least three forces acting on at three distinct points, which means not all members are zero force members. Now the yellow structure that I am showing here is a frame. Is there at least one member which is having at least three forces acting on it? There is one. We will see this. Now in this yellow structure, BE, member BE, this member, CEF, another member, and ABCD are individual rigid body members. Joints C, B, E are pins. C, B and E are pins. Support at A is also a pin joint, and GD is a cable. So there are three members. If you pay attention to member BE, that member is a two force member. BE is a two force member. But you may say that, okay, at B there is a force, at E there is a force, but there should also be the self weight of the member. Then why am I calling it a zero force member? I'm calling it a zero force member because I am working with this approximation that the self weight of all the members in a frame is negligible. Negligible to what? Negligible to the other forces that appear on these members. Compared to those other forces, the self weight is zero. So this member may have a mass of say 1 kg. So what is the weight? Almost 10 newtons. But the kind of forces that could appear at the joints, or the kind of force that is hanging on from the frame, that may be in kilonewtons. The weight that the frame is withstanding is much more than the self weight, and that is why on an FBD of any of the member, the self weight, you put it there or you don't put it, it won't affect your analysis much. Okay, so with this approximation that AD, CF and BE, AD, CF and BE are all lightweight members, I am claiming that member BE is a 2-force member. Member CEF is a 3-force member. Again, I am not counting the weight of CEF, but even discounting the weight, you can observe CEF. There are 3 points. One is C itself, the other is E, and then there is a weight hanging at F. So there are 3 forces acting at 3 distinct points of CEF. Thus, CEF is a 3-force member. The moment you identify at least one 3-force member, you can go ahead and declare that the structure that you are dealing with is a frame. Okay. For sake of completion, I have written here, member DCBA is a 4-force member. One force coming from the cable at D, another from the pin joint at C, another at B due to the pin joint, and the last one at A due to the pin joint at A. Now, having understood what a frame is like, now I want to do analysis of frames. What is meant by that? Given an applied force system, finding number 1 reactions at supports, in this case here, and then forces acting on individual members CEF, BE, etc. I want to know on each member how much force is acting. This whole thing is called analysis of frames, finding these forces. Note that no 2 members in a frame interact directly. You can think of this as an approximation. In reality, if you put one member like this on top of the other one and you put a pin joint, you can argue that there will be maybe some friction force acting between the 2 members directly without the pin. In reality, it will happen, but we are doing an approximation here for analysis. And we are saying that no 2 members interact with each other directly. They interact through the pin that joins them. So member CEF will interact with this pin here. If I am talking about member BE, at B, member BE interacts with the pin, this pin, and member in the background, which is ABCD, also interacts with that pin. But there is no direct interaction between this member and this member. This is what we are assuming. Okay. Now, keeping this point in mind, we will be drawing free body diagrams of various members. And those free body diagrams of various members should be consistent with each other in the light of Newton's third law. I will elaborate on this. In fact, I will consider 3 cases and draw free body diagrams of various members and pins separately. Case 1 is only 2 members are connected by a pin. Case 2, more than 2 members are connected by a pin. And case 3, 2 members are connected by a pin and an applied force acts on the pin. Case 1. There are 2 members of the same frame interacting through a pin here. Now here I have shown truncated FBDs. I am showing you truncated FBDs. Truncated means this AB is maybe connected to some other members also here, may be connected to another member. This may be connected to another member here. My interest is not to pay attention to these members. My intent is to pay attention to this zone of the frame, truncated part of the frame, and thus I will draw truncated FBDs. So we have a situation, 2 members interacting with a pin which is joining the 2 members. If you draw the truncated FBD of AB, I will put a force, one unknown scalar in y direction, one unknown scalar in x direction, and the vector B, which will have these 2 components, that will be the force vector exerted by pin on AB. Have this clarity. B is the force vector exerted by pin on AB, not by member BC on AB, because I am saying member BC does not interact with AB directly. So there is no force coming from BC on AB. The only force that comes on AB is because of the pin B, and that pin is exerting force vector B, components Bx and By. Now let's go to the truncated FBD of BC, the other part. I am putting 2 unknown scalars, Bx prime and By prime, and the corresponding vector B prime will be actually the force exerted by pin B on BC. Not by AB, not by member AB, by pin B on BC. Same reasoning, BC is not interacting with AB directly. Okay, B and B prime, 2 forces, 2 force vector. Now let's draw the FBD of pin B, pin B itself. So pin B is dealing with AB on one side and dealing with BC on one side. AB is exerting a force, BC is exerting a force on it. The force that AB exerts will be minus B, and that is why you see here I had Bx and that has become Bx on the left hand side, going from right to left. Here it was from right to left to right. Here I had a force By in positive y direction. I have put a force By in minus y direction. Okay, so these 2 components are coming from AB on the pin. Similarly, these 2 components are coming from BC on the pin. So now if I do the force balance, Euler's first axiom, for this pin itself. Okay, what do I get? Bx plus Bx prime 0, which means Bx prime is minus of Bx, and then By plus By prime equals 0, which means By prime is minus By. Now if I use these two conclusions and come back to this FBD, I can draw this FBD like this, where I have put a force Bx which is equal and opposite to force here, By which is equal and opposite to By here. So if you are dealing with a case when there are only two members interacting through a pin in a frame, even though the two members do not interact directly, the detailed analysis is leading me to a conclusion which I can present as what is written here. We can pretend, actually it's not happening, but pretend AB and BC are interacting directly and bypass drawing FBD of pin explicitly in your analysis. If it is case 1. Case 1, By, Bx, opposite Bx, opposite By, end of story. We can pretend that two are interacting directly. Let's have a look at case 2. Case 2, I have 3 members of a frame and they are all connected by a pin here. And as before, no two members are free to interact with each other. Everybody is facing the pin. The pin is tackling, in a manner of speaking, handling all the members. It's like a manager dealing with 3 different employees. If I draw truncated FBD of AB, like before, I put Bx and By, and if I ask you who is exerting Bx and By, you should be able to tell me. Pin on, by pin on AB. Fine. I go to the next member, FBD of BC. I put Bx prime, Bx B prime, vector is B prime, by pin on BC. And then I go to BD and I put Bx double prime, By double prime, the vector is B double prime, by the pin on BD. Okay, now let's go to the FBD of the pin itself, the manager. What is the free body diagram of the manager? The free body diagram of the manager will be what I have drawn here. And mind you, again, like before, Newton's third law is being applied. Since I put Bx going from left to right, here Bx comes right to left. Since By was put here going upwards, By comes as downwards. Since Bx prime left to right, Bx prime comes from right to left. Since By prime was upwards, By prime is downwards here. Pay attention to this. If you do not ensure this consistency, if you put Bx here on the pin like this, you will not get the right answer in your analysis. So do be careful about this consistency. Okay, so having put all the forces on the pin following Newton's third law, I apply Euler's first axiom to the pin, and these are the two equations I get. Bx plus Bx prime plus Bx double prime 0, and similarly By, By prime and By double prime 0. Now in this case, there is no way to pretend anything else than what the reality is. The reality is that pins interact with the members don't interact with each other, and that is why you will have to draw the pin FBD. You cannot escape that. Contrast this with what happened last time. I drew the FBD of the pin, I got the right conclusions, but then I said those conclusions can be drawn anyway if I pretend AB and BC were interacting directly. You will still get the right answer. Here, there is nothing to pretend. You will have to deal with FBD of pin B and relate the three scalars in this manner. Okay, FBD of pin must be drawn in this case, and summation of Fi should be used with pin B as the system in two directions. If it is a 3D frame, in all three directions. I am considering it to be a 2D frame. I am assuming the force system is planar for illustration. If the force system is not planar, then similar things will happen with the Z component of the forces as well. And you will add one more equation here. Bz plus Bz prime plus Bz double prime 0. Things like that. This will come. Not planar. Okay. Case 3. Case 3 is when there are two members interacting through a pin and then somebody has directly applied a force on point pin B. Applied a force on pin B. You draw the truncated FBD of AB with Bx, By, that of BC, Bx prime, By prime, and then of pin B, you will have Bx, Bx prime, opposite directions, By, By prime, opposite direction, and then that extra force that has been applied on the pin directly, load. That could be the load, applied load. In fact, I have put two forces, PQ, and that's why both forces are appearing. And in this case, applying Euler's first axiom to the pin, this is the relationship that exists between Bx, Bx prime, By and By prime. Can we pretend that the pin does not exist? No, you cannot. In this case also, the FBD of the pin B is absolutely necessary to complete your analysis. For the three cases that I showed, only first case allows you to ignore the FBD of pin B and get the right conclusion. For the other two cases, FBD of pin B is absolutely necessary. Analysis of frames, what would be the approach? Consider entire frame as an FBD. Write equations of equilibrium, find reactions at supports. First, you should try to find the reaction forces at the support. Second step is to draw FBD of an individual member of interest. Write equations of equilibrium for that member, find some unknowns. If the number of unknowns exceeds the number of equation, consider FBD of an adjacent member. Write its equations of equilibrium of the new member and see if the desired unknowns can be found. Every time you draw the FBD of a new member, you get access to 6 scalar equations. If it is a 3D problem, if it is a 2D problem, every rigid body comes with its 3 equations all the time. So whenever you are falling short of equations, keep going to the adjacent rigid bodies and keep adding equations till you match the number of unknowns to the number of equations. That's what I have written. If still number of unknowns does not match or is more than the number of equations, repeat step 2. What is step 2? Draw FBD of an individual member of interest, the next individual member of interest. And while you draw several FBDs, keep this point in mind. Following Newton's third law, consistency among all FBDs must be maintained strictly. If you don't do that, you will not get the right answer. Okay. Let's have a look at this example. Analysis. We have been given a frame, and this frame is supposed to withstand this much load. That's why this exists. The purpose of this frame is to be able to withstand this load of 480 newtons. Okay. This may be holding a balcony or a platform or a dais, something like that. There are two supports. One is the pin joint here, the other is a roller support. Is this a frame? First question is this really right to call it a frame? How do we test that? Frame or not? At least one member with at least 3 forces. Exist or not? Look at member BCD. Before that, let's count how many members we have. I don't know whether the screen resolution is good enough on your side or not. This is one member. This is one member, one rigid body. RB1 you can call it. This is RB2. There is a member here. RB2. Okay. Another member, RB3. Pins. One pin is here, pin 2, pin 3, pin 4, pin 5. 5 pins. Three members. Self-weight negligible, but very much capable of carrying high loads, 480 newtons. Supposed to withstand. Load bearing structure. That's how I introduced this concept, right? Load bearing structure. This is the load. The structure is, of course, the frame. So is this a frame? If I focus on RB2 and try to see whether it's a what kind of member is this? RB2 is this. This is RB2. The green color thing here. Here the green color thing. RB2. There is a force here. There is a force here. And there must be a force here. So there is at least one member with at least 3 forces acting. And that makes the entire structure a frame. Structure is a frame. What do they want us to find? Specifically here, they want us to find force in member ED. Force exerted on BCD, at point C, at pin C. Two things they want us to find. Now we can start doing the analysis, but there is an interesting part in this problem which I want to highlight. This structure is a frame indeed, but there is one two-force member in this, hidden. RB1, RB2 and RB3. RB2 is clearly not a two-force member. RB1 is also not a two-force member. If you look at RB1, FBD, if you try to draw, there will be a force here which we call as FA. There will be a force at FC, and then there will be a force at E. Not a two-force member. But if you look at BED, look at DE or ED. One force at E, one force at D. Two-force member. Every frame doesn't have to have any two-force member. There is no restriction like that. But this one happens to have one two-force member, RB2. Now what is the significance of identifying a zero-force member in a frame? The significance is that the moment you know that a particular member is two-force member, you know that these two forces will have equal magnitude and they will be either pointing towards each other or pointing away from each other. Because this whole thing is in static equilibrium, ED is also in static equilibrium, and I know from my understanding of a two-force member that if it has to be in static equilibrium, the forces on the two sides must be equal and directed towards each other or going away from each other. In this case, since the member is, in this case you actually know that it will be, if I talk about now BCD, the force coming from the pin that is connected at here at D will either like this or like this. The magnitude is unknown, but the direction is known. Okay, the direction of this force will be along ED. So I can modify this and write it like this, where this angle is known, and I have just one unknown scalar here. That unknown scalar can be found while considering the BDs of the other bodies, but only one unknown scalar. Okay. I am not going to solve this question fully. I wanted to solve this question during the lecture session. Okay. However, I don't think I can finish it in next 10 minutes. So I leave the matter here itself. I would declare that